Hi, I'm Frank. Welcome to the Piezo-Metrics channel. I thought I'd do something different today. Let's see what happens when I put some butane into this bottle of water. So put about 25 milliliters of liquid butane into about 800 milliliters of water. It'll take about 30 seconds. Here we go. That was pretty impressive. The speed that the bottle exited the tube was pretty dramatic. So, how is the pressure generated by the butane? Suffice to say that the pressure comes from the butane expanding rapidly as it passes through the warmer liquid in the bottle. There is no chemical reaction between the butane and the liquid. It'd be interesting to measure the pressure and thrust caused by the expanding butane in the bottle. So let's do that with Piezo-Metrics strain gauge rosettes. We'll go through several steps to make the measurements. First, we'll gauge a water bottle with two bend rosettes to measure the pressure in the bottle. And then we'll gauge a cantilever beam with two bend rosettes to measure the thrust. Then we'll wire up the rosettes to form open bridges for the pressure and the thrust bridges so that we can measure their gauge resistances. And then we'll measure the gauge resistances at 0 and full scale pressure, at ambient, cold, and hot temperatures. With the data in hand, we'll calculate the temp comp solution using Piezo-Metrics online temp comp calculator and then wire up the closed bridges. After that, we'll put our water bottle in a test stand, fill it with butane, and repeat the launch sequence to measure the pressure and thrust time profiles on a test stand. Lastly, we'll look at the results. So, for the first step, here are the materials we're going to use. First is our bottle with the rosette positions marked out. The surfaces were lightly sanded and wiped with IPA. I filled the bottle with water to make the wall stiffer. Here are the two bend type rosettes for the pressure measurement ready to go. I have another two bend type rosettes to make the thrust measurement. The rosettes are mounted on transparent tape with the solder pads sealed. M-Bond 200 catalyst has been applied. Here is the magnet wire I will use to create the open bridges. Here is the terminal strip I will use to connect the gauges to the instrumentation cable. Here is the instrumentation cable. And here is the M-Bond 200, which is a cyanacrylate adhesive. As you can see, I decided to build a dam around the gauge area with tape to keep the M-bond from spreading out too much and making a mess. So first, I will position one rosette on the side of the bottle. The two parallel gauges are oriented along the axial direction. Then I will apply a drop of M-bond. And then I'll bond the rosette to the bottle. With that done, I'll repeat the same procedure on the other side and also bond the terminal strip. I won't show that here because the procedure is the same. After the requisite 90 seconds of applied pressure and 90-second wait, I can now peel the tape off the rosettes and terminal strip. I can also peel off the tape, making up the temporary dam. I already peeled the tape off the rosette on the other side of the bottle. Here is our cantilever beam for the thrust measurement. The way it works is this end is held rigidly in a support, and this end is free to move. The bottle is placed into this holder. When the butane gas is expelled, a force is created on the holder and acts as a moment on the beam that bends the beam. I will be installing the bend rosettes on the top and on the bottom of the beam. I have positioned the top bend rosette on the beam. I will apply a drop of M-bond and bond the rosette to the beam. With that done, I'll repeat the same procedure on the other side and also bond the terminal strip. I won't show that here because the procedure is the same. After the requisite 90-second pressure and 90-second wait, I peeled off the tape. Here is the gauged beam. Now we come to wiring our gauges to form an open bridge. Here's a diagram of an open bridge. We have a terminal strip with terminal colors red, white, black, yellow, and green. I pre-cut and pre-tin the magnet wires and pre-tin the solder terminals. I was careful not to let too much heat soak into the plastic. So I'll make a few connections here to demonstrate. Here we have gauges G1 and G2. G1 is axial and G2 is hoop. You can see I have taped the wires down to make the soldering quicker and easier. I'll continue to solder the rest of the wires to complete the open bridge. I won't show that here because the procedure is the same. As you can see, I messed up on one of the rosettes. I applied too much heat on the solder pads and they came off. When soldering, the solder iron tip should only be on the pad for a fraction of a second. So it's quite important to pre-tin all contact points. There's no time to add solder. To make sure there were no problems to solder on the instrumentation cable, I already soldered on a couple conductors. I'll finish that up now. With that done, I'll do the same thing for the thrust measurement bridge. I won't show that here just to speed things up. To finish, here are the two open bridges wired up. One is to measure the pressure in the bottle, and the other is to measure the thrust generated. I should also mention, when soldering on the wires, it's important not to pull on the wires afterwards, because there is a good chance the solder pads will peel off. Here are the components that I'll use to get a temperature compensated, calibrated output from our pressure bridge. I'm hoping that I'll be in the right ballpark because I'm using a tire inflator, that's a pressure source, and a somewhat leaky pressure coupling for this measurement. The gauge bottle is filled with room temperature water and put into a plastic bag. The bottle and bag are in this insulated water carrier that is also filled with room temperature water. I let the water temperature stabilize to about 75 degrees Fahrenheit. The instrumentation cable is connected to this Keithley DAC 6510 that is set up to read the gauge resistances. The Keithley will read the resistances first at 0 pressure, then at a full scale pressure of about 7 to 8 psi, and then 0 pressure after I release the pressure. You can see the resistance traces on the Keithley. All 4 resistances are going up with pressure, as they should be. With that done, I'll repeat the procedure with cold and hot water. I won't show that here. The procedure to temperature compensate the beam is the same as what I used with the bottle. Here are the components that I'll use for the moment beam. The beam is at room temperature. The instrumentation cable is connected to the Keithley as before. The Keithley will read the gauge resistances first at 0 load, then at a full scale load of 1000 grams, then at 0 load. I'll be adding weights to the bottle holder to represent the thrust of the butane boiling off. You can see the resistance traces on the Keithley. The top gauges are showing lower resistances because they are going into compression. The bottom gauges are showing higher resistances because they are going into tension, as they should be. With that done, I'll repeat the procedure at cold and hot temperatures in a thermoelectric cooler. I won't show that here. Now that we have our gauge data, we can calculate the temp comp solution for the pressure. I put the data in the required format in a CSV file. I'll first specify a 5-volt excitation and a 0.1 volt full-scale output. I'll upload my file for data verification. I'll use the axial data category because I'm measuring the axial and hoop strains on the bottle. Criteria 4 and 5 are necessary to obtain a solution. To understand why, I suggest watching the video on temperature compensation using a passive resistor network. The link is given below. Criteria 4 says the resistances at 0 load increase with increasing temperature. And criteria 5 says the output at full-scale load decreases with increasing temperature. Both of those are okay. As for the rest of the criteria, they're less important. I'll go on to calculate the temp comp solution. We see that RB2 is 100 ohms, RZ4 is 2610 ohms, RS is 649 ohms, and RP is infinite, which means it's not needed. Going over to the predicted bridge outputs, we see that at 0 load, the output varies between 0.1 millivolts and 2 millivolts. The full-scale outputs vary between 94 millivolts and 97 millivolts, which is pretty decent. Let's download the PDF. I'll do the same thing for the thrust data. I'll specify 5 volts as before. You may notice that I've entered 0.8 volts for the full-scale output. There's a reason for that, but I won't go into that here. I'll upload my file for validation. I'll use the bin data category to validate the data. Again, criteria 4 and 5 are necessary to obtain a solution. The resistances at zero load increase with increasing temperature, and the output at full load decreases with increasing temperature. So that's good. Going on to the temp comp solution, we see that RB2 is 332 ohms, RZ4 is 1100 ohms, RS is 287 ohms, and RP is not needed. Looking at the bridge outputs, at zero load, the outputs vary between about 3 millivolts and about 10 millivolts. For the full-scale outputs, they vary between 90 millivolts and about 120 millivolts. These results are not ideal, but it's okay for this demo. I'll download the PDF. At this point, I'll go ahead and put together a breadboard that will build the temperature-compensated bridges to measure the pressure and thrust time profiles. Let's make some pressure time and thrust time measurements with this test setup. The output from the gauge bottle and the gauge moment beam are fed to our temp comp circuitry, which is then fed to our Keithley 6510 data acquisition system. The Keithley has a maximum acquisition rate of about 40 Hz per channel, which is a bit on the low side, but we'll have to make do with that. The setup is powered by this Jacquerie power station. It provides the 120 volts AC to our Keithley and the 5 volt DC to our bridge circuits. Now this test stand allows me to fill the bottle with water and butane, and then lets me flip it down quickly, just like I did when I launched the bottle. So right now there's already 800 milliliters of water in the bottle. I'll put 25 milliliters of butane, like I did before, and so it'll take about 30 seconds. Once that's done, I'll hit the trigger for the data acquisition system and make our measurements. So I'll fill the bottle first with butane. Trigger. Where are you? That was quick. Here's the captured data. The green is the pressure and the blue is the thrust. I'll look at it more closely offline. Here are the pressure time and thrust time profiles from the testing. The scale for pressure is on the left-hand side of the graph, and for thrust it's on the right-hand side. Pressure is the blue curve and thrust is the orange curve. The initial bump in the thrust data was caused when I tipped the bottle over. After converting the voltage readings into engineering units, we can see that we reached a peak pressure of 37 kilopascals or 5.4 psi. For thrust, we reached a peak thrust of 17 newtons or 3.8 pounds. The total duration of the pressure event was about 0.6 seconds. As a secondary check of these measured quantities, if I divide the thrust by the pressure, I can calculate the area of the bottle opening and therefore the diameter of that opening. When I did that, I got a deduced diameter of 24 millimeters. Now, the actual diameter of the bottle opening is 22 millimeters. So, despite the fact that I measured strains in two polymeric structures, and I temp comped them using consumer-grade load and thermal conditioning equipment, and I used two independently measured parameters, namely pressure and thrust, I have to say that I'm pleasantly surprised I was able to calculate a bottle opening diameter that was within 10% of the actual bottle opening diameter. Now, since I have a thrust time profile, I thought it would be interesting to calculate a flight profile for the bottle. To do that, I'll use Newton's second law of acceleration, or F equals ma. As this equation shows, we have mass times acceleration on the left-hand side. And on the right-hand side, we have the summation of forces consisting of the time-dependent thrust, the force of gravity, and the drag force acting on the bottle. Since gravity and drag are acting against the thrust, they have a negative sign. The differential equation can be solved for velocity using the Runge-Kutta method. The height is obtained by integrating the velocity-time profile. When I put in values for the mass of the bottle, the thrust versus time data, the coefficient of drag, and the frontal area of the bottle, I got these results. The left-hand scale is height in meters. The right-hand scale is velocity in meters per second. The orange curve is velocity, and the blue curve is height. We can see that the bottle is predicted to reach a maximum velocity of about 35 meters per second in 0.6 seconds. A maximum height of 28 meters in about 1.8 seconds, and a total flight time of approximately 5.5 seconds. These flight results don't match very well what I observed when I launched the bottle. The only definite measure that I have is that the total flight time was about 3.5 seconds. I'd only be guessing if I gave a number on how high the bottle went. There are many reasons why there is such a discrepancy. For example, the bottle did not fly straight up like this simulation assumes. Also, I may not have injected as much butane in the bottle for the launch as I did on the test stand. At this point, it isn't worthwhile to continue pursuing the causes of these discrepancies. There are just too many parameters that I didn't characterize directly. It's interesting to make this calculation, though. In this video, I've attempted to show how a Piezo-Metrics rosette can be used in a practical application like measuring the pressure in a pressure vessel or measuring the force acting on a load sensor. I showed the steps involved with gauging and wiring the parts, measuring the open bridge gauge resistances, and temperature compensating the bridges using Piezo-Metrics temperature compensation calculator. The pressure and thrust measurements from the temperature compensated bridges on the test stand actually worked out pretty well. If you'd like more information about the techniques that I used in this video, please refer to the links given in the description below.